Martin, and this is my physics lab 3, the black hole. The purpose of this experiment is to find the mass of a black hole using a planet's orbit and then determine the initial velocity a ship must have to approach and pass the black hole without crashing into it. The resulting mass of the black hole was 1.11 e to the 34th kilograms, and the initial velocity of a spaceship is negative 5.032 e to the 6th in the x direction and 1.405 e to the 7th in the y direction. The two main concepts presented were Newton's second law and universal gravitational pull. Newton's second law describes how forces affect the system, and the accumulation of these said forces is the net force. In this experiment, the two forces were a parallel and perpendicular force, and universal gravitational pull being the parallel force. And as those add together, they equal the net force. And universal gravitational pull, as stated, is all objects have this, and the bigger the size, the bigger the attraction, and it's calculated by this equation, as we'll see later in my code. Here's the glow script that I used to calculate the mass of the black hole. On this side, we're calculating the two forces, the parallel and perpendicular forces, and then over here we're using the equation as shown earlier that calculates the mass of the black hole. The net forces of the parallel and perpendicular are shown here, and the mass, as stated earlier, is 1.11025 e to the 34th. Here's a quick video showing the forces acting upon it. This is the perpendicular force, and this is the parallel force. And as described, the second part of this experiment was to calculate the initial velocity that a spaceship needs to have to approach and pass the black hole from departing from the planet without crashing into it. In this glow script, you have the gravitational pull on the planet, which shows the gravitational pull from the black hole, which is the majority, and the small gravitational pull that the spaceship has on the planet as it departs. Here's the gravitational pull on the ship from the planet and the black hole, which both are significant in this case. And on this side, we're calculating the the position of the spaceship and the planet at each time using WT and the velocity. As stated earlier, the initial velocity is negative 5.032 e to the 6th and 1.405 e to the 7th in the y direction. Here are my results. As you can see, the spaceship is in magenta and the planet is in cyan or blue. As it approaches the black hole, it slightly passes it without crashing into it and continues on to its way. And it took this much of the orbit of the planet to accomplish that. So possible sources of error. This experiment could contain some possible sources of error or become more accurate in both parts. In the first part, since I calculated the mass of the black hole by all of the given masses at that time period and using the average, then running the program longer and getting a larger sample size would give a more accurate set of results. In the second part, the initial velocity was calculated through a trial and error, so it was also an estimate and not an exact number. And further questions: how are the net force and its parallel and perpendicular components different from the rate of change and its parallel perpendicular components? Even though they are equivalent mathematically in this case, since they are both products from the overall force acting upon it, but the rate of change is a more observable term, and it relates to the object's position and velocity, where the net force is the sum of all the forces acting upon it and cannot be known without other mathematical units like the mass of an object. The second question: what initial velocity would your spaceship need in order to enter some kind of orbit around the planet instead of looping around it? The initial velocity of the ship would have to be closer to even, and to a lower degree in the x and y axis, as it would be a mirror of the planet's orbit almost. An example of this velocity would be negative 2.7 e to the sixth and 1.08125 e to the seventh. And yes, thank you guys.